So hi everyone, today we are going to use the NP fundamental lemma that we have learned in the last lecture to see how one can use these fundamental lemma to estimate some parameters or test some hypothesis. So we will do that. So what is the NP lemma? The NP lemma tells us, suppose that for P0, suppose there is a null hypothesis P0 against a alternative hypothesis H1, there always exists a test phi and a constant k such that the expectation of the test will be the alpha, and the test will be we will reject the null hypothesis with probability 1 when p1x is greater than k p0x, and will reject the null hypothesis with probability p when p1x equal to k p0x, and we will accept the null hypothesis when p1x is less than p0x. So this is the Neyman-Pearson fundamental lemma. So now we are gonna use this to test some useful hypothesis of normal distribution. So let's do it. Example. Suppose that x1, x2, xn follows a normal distribution with mu and 1. Now we have to test the hypothesis H0, that mu equal to 0, against the hypothesis, alternative hypothesis, mu equal to 1, and we have to find IMP test. To find the MP test of alpha equal to 0.05. Now we know the distribution of normal x will be so the distribution of these n random variable will be f x bar. Here this means x1, x2, xn mu will be, since they all are identically independent random variable and they have taken from identically independently and from a same distribution, then we can write the joint distribution as the multiplication of this n random variable, and we know the normal distribution for any single random variable will be 1 by root 2 pi sigma. Here sigma is 1, e to the power minus 1 by 2 sigma square x1 minus mu x square. So it will be 1 by root 2 pi e to the power minus half xi minus mu h square. Let's simplify it, then it will look like root 2 pi to the power n e to the power minus half summation of I equal to 1 to n xi minus mu h square. Then under the null hypothesis, what this distribution, how this distribution will look like? The distribution will look like x bar mu equal to 1 by root 2 pi to the power n a to the power minus half I equal to 1 to n. We have to put mu equal to 0, so that is xi square. Now under the alternative hypothesis, how does the distribution look like? That will be 1 by root 2 pi n e to the power minus half summation of I equal to 1 to n xi minus 1 square. Now from the MP from the Neyman, according to the NP fundamental lemma, most powerful test of a given size alpha is reject the null hypothesis if 1 x mu by f0 x mu greater than k. So that means if I put it here, it will become e to the power minus half summation of I xi minus 1 square e to the power minus half summation of I xi square greater than k. So 1 by these two this is cancel out, 1 by root 2 pi and 1 by root 2 pi to the power n. Let's expand the upper term, e to the power minus half sum over I xi square minus 2xi plus 1 into e to the power half summation of xi square greater than k e to the power minus half I xi square into e to the power half summation of xi square into e to the power plus summation of xi into e to the power minus half greater than k. So these two cancel out, this will become, and if I adjust this constant in the right hand side, it will give another constant equal to greater than some k prime. Or you can take log both sides, so it will give xi is greater than some log k prime, and it's again a constant, so this will be summation of xi is greater than some other constant. Now let's redefine our variable, like this is Let's 1 by n summation of xi greater than k double prime by n, it will be x bar. Now multiply it with root n, that will become root n k double prime. Now you see, okay, that will become like 1 greater than root n. So this is a constant. Suppose C. Now probability of type 1 error is alpha, and what is this? This probability of reject null hypothesis, that is H0, when it is true. Is alpha. That means under the probability distribution F0, and when we will reject the null hypothesis, when this condition will satisfy. Under the null hypothesis, when root n x bar will greater than C. Under the hypothesis H0, this is equal to alpha. And we know that these if x1, x2, xn follows a normal distribution with mean mu and variance sigma square, the x bar, which is summation of I equal to 1 to n xi by n, will follow, and this will follow root n x bar minus mu by sigma will follow a normal, standard normal with standard normal distribution. So this is, since here sigma equal to 1 and mu is, this is a standard normal distribution, so that means we can write it P H0 Z greater than C equal to alpha. Now you see, this is a distribution, then the probability, suppose this is z axis and this is f of z. Now the probability that z greater than C is alpha. What this point is called in standard notation, this is called z alpha point of the standard normal distribution. So this is, that means C is z alpha point, and we know the value of z alpha, since it is given that the significance is alpha is 0.05, that's why. And from the table of the standard statistics books, we know that z alpha alpha equal to 0.05 is 1.645. So that means if root n x bar greater than equal to, so here I means anyone can be confused by the things that in the previous step there is only a greater than sign, and in the next step I add a equal sign. But you don't confuse, because you see, for a continuous distribution the probability to find a particular point, that means probability of C will be 0, because probability of particular point is 0. Probability of finding particular, since you know that probability of C is probability distribution integration dx. So here you have to integrate from C to C, that will be 0. So probability of finding a single point in the continuous distribution is 0. That's why this equality doesn't matter. So you can add the equality, that's it. That will not change anything. So if root n x bar greater than C, that is Z alpha, means 1.645, we can easily, if root n x bar is more than 1.645, we can easily reject the null hypothesis. We can reject the null hypothesis. So this is the most powerful test. So let's move towards another example, and here mu is not 0, but mu is suppose, and mu is suppose something. So let's see it. Another example is, suppose that x1, x2, xn is follow a normal mu 1 distribution. So suppose, no, let's see, this is another example where I gonna hypothesize the standard deviation. So it follows a 0 sigma square. Now my hypothesis is, null hypothesis is that sigma square equal to sigma 0 square against the alternative hypothesis, that is sigma square equal to sigma 1 square. Now again, from the previous example we know what is the distribution function. Let me use another color. So probability distribution under the null hypothesis is that I will means I have to write the joint distribution. So joint distribution of this n random variable. So that is, since they all are identically independently, they are IID random variable, that means they all are identically distributed and all are independent. So that are I equal to 1 to n 1 by root 2 pi sigma 0 e to the power minus 1 by 2 sigma 0 square summation I equal to 1 to n xi square. Now see what is the alternative distribution, probability distribution under the alternative hypothesis. That will be f1, that is I equal to 1 to n 1 by root 2 pi sigma 1 e to the power minus 1 by 2 sigma 1 square summation I equal to 1 to n. Now guess what we'll do, and you guess right, I think. We will apply the Neumann-Pearson fundamental lemma. according to NP fundamental lemma, that is fundamental lemma, the most powerful test is reject H0 if f1 x bar by f0 x bar is greater than k. Let me see that it is working or not. It's working properly. Okay, if and this, so put all the things together and okay, this is not right, so this is to the power n, this is to the power n, so that means if we divide it, it will get sigma 0 to the power n, sigma 1 to the power n, e to the power minus 1 by 2 so this will be summation 1 by 2 sigma 1 square minus if you divide it, so it will be plus, so 1 by 2 sigma 0 square sum over I equal to 1 to n xi greater than k. So this is a constant, so anyone can adjust this left hand side constant to the right hand side constant and we'll get another new constant. Suppose that constant is half 1 by sigma 1 square minus sigma 0 square summation xi I equal to 1 to n. Suppose that is k prime. Now take log, you will get that minus half sigma 1 square minus sigma 0 square I equal to 1 to n xi. And this half is again a constant, we can adjust it here, so you will get 1 by sigma 0 square, so 1 by sigma 0 square minus 1 by sigma 1 square 1 by sigma 0 square minus 1 by sigma square summation of I equal to 1 to n xi greater than 2 k prime. Now you see xi square, I think this is xi square, this is square. Now you see, depending upon whether sigma 0 square less than sigma square 1 square or sigma 1 square less than sigma 0 square, you get a condition of rejecting the hypothesis. Suppose this condition is here, so that means now here that means this is positive number 1 by sigma 0 square will be greater than 1 by sigma 1 square, so this is positive, the relation will be same. And if this is true, that is 1 by sigma 1 square will be greater than 1 by sigma 0 square, so this is a negative quantity. Now you see, suppose this is I am let work with this condition. So if you do, this will become summation of I equal to 1 to n xi square less than some other constant. Suppose this is C. Now this is the condition for which will reject the null hypothesis. So then what will be my type 1 error under the hypothesis H0? This condition is true, that is I equal to 1 to n x square less than C. And we know that summation of xi square, summation of not this, summation of xi minus mu square by sigma square follows chi n square distribution, or you can write it is as, since here mu is 0, this means xi square by sigma square actually follows a chi square n distribution. So this means probability of H0, that's divided by sigma 0 square 1 to n x square by sigma square less than some another constant, suppose C naught is alpha, and suppose this variable is w, then w is less than C0, that probability is alpha. Now you see, suppose this probability is alpha, because if this is w, this is fw, then this probability, suppose, and this is will be square n 1 minus alpha point, because the less than of these will be C, less than the probability that any random variable will be less than this is alpha, and greater than this is 1 minus alpha. So this is, this C0 is chi square n 1 minus alpha. So our test is reject H0 if I equal to 1 to n x square by sigma 0 square less than chi square n 1 minus alpha. That's our most powerful test. For testing hypothesis of sigma square. That's it. Now let's see another example where I will not use the Gaussian normal distribution. We again use a exponential distribution. So one example, another example is suppose our random variable xn, x2, xn follows, and identically distributed random variable which follows a probability distribution function equal to lambda e to the power minus lambda x, where x greater than 0 and lambda greater than 0 and 0 otherwise. Now here our hypothesis is, null hypothesis is lambda is 1 and alternative hypothesis is lambda is 2. Now again here these two are simple hypothesis, these two are simple hypothesis. So we can easily apply Neyman-Pearson lemma according to NP fundamental lemma the most powerful test is reject H0 if F1 joint distribution by joint distribution under the null hypothesis is greater than some constant greater than k. Now let's see under the null hypothesis what the joint distribution will look like. How it will look like? It will look like pi equal to 1 to n lambda e to the power minus lambda xi. So this is the distribution. Now how it will look like under the null hypothesis, that is x bar 1, that is simply I equal to 1 to n 1 to the power minus xi. So this is e to the power minus summation of xi, and under the alternative hypothesis that will look like pi equal to I to n 2 e to the power minus 2xi. So that means 2 to the power n e to the power minus 2xi. Now under this condition, if we put the distribution f0 and f1, we'll get a to the power 2 to the power n e to the power minus 2 summation of xi by e to the power minus summation of xi greater than k. So this is again a constant, so we can write it's like that, minus summation of xi is greater than some k prime. Now if you take log, then negative of xi will be again some another constant. That means if summation of xi is less than some another constant c, we will reject. Now let's calculate, if it is the test, what is the type 1 error, the probability, that is reject H0 under the hypothesis H0 is alpha. So when we'll reject, if probability under H0, if these condition satisfied. Now the sum of so under the null hypothesis, you see the distribution becomes e to the power minus x for x greater than 0. So this is a exponential distribution with mean 1. Under the means the summation of xi actually follows a gamma distribution if I equal to 1 to n with n and lambda. Now so this is y will follow. So under H0 null hypothesis, y will follow gamma n1, and fy is 1 by gamma n e to the power minus y to the power n minus 1. Now if you change the variable, 2y is w, you'll get f w is 1 by 2 to the power n gamma n e to the power minus w by 2, and this is w to the power n minus 1, and this is nothing but chi-square 2n distribution, chi-square 2n distribution. So that means if this is y, so if we multiply both side by 2, you will get another constant. So this is summation of xi less than some c naught is alpha, and you know this 2y follows a chi-square distribution. Suppose this is w, so p h0 w less than c0 is alpha, and we know w follows chi-square 2n distribution. Now if w, the probability that this random variable is less than a constant value, that probability of that thing is alpha. So let's see it pictorially. So this is, so suppose this point is c naught, then the probability of these, the w, suppose this is w and this is fw, so probability less than c naught is alpha, and probability greater than c naught will be then 1 minus alpha. So c naught will be chi-square 2n 1 minus alpha point. So the test is reject the null hypothesis if 2 summation of xi is less than or equal to, since this is a continuous random variable, equal to sign doesn't matter here. You can give the equality sign or you can't. So chi-square means if you want you can give the equality sign, or if you don't want you can remove this equality sign, that's it. Square yes 1 minus alpha. So that's it. This means here 2n, n is the number of variables and x bar is the sample mean. If less than chi square 2n minus 1 minus alpha, we will reject the null hypothesis. Let's see conceptually does it make sense or not. So we know this lambda, this if you calculate the expectation value, that mean, suppose what is the mean of this distribution, integration 0 to infinity lambda e to the power minus lambda x dx, that will be, suppose lambda x equal to z, so then 0 to infinity to the power minus z dz, that is x. So 1 by lambda into lambda x, so that will be z dz, 1 by lambda, so this is 1, so 1 by lambda. You see the mean is 1 by lambda, so lambda is less means the mean is more, right? So lambda is less, if lambda is less, that means mean, that means summation of x by more. So if lambda is more, that means if lambda is higher, mean should be lower. So for lambda equal to 2, the summation of the sum of the xi's or the mean should be less. So mean should be lesser than the lambda equal to 1. So that's why the test making sense, because it tells if your mean is less than some value, you cannot, your hypothesis cannot be accepted, because you see that is in the regime of the second hypothesis, lambda equal to 2, because for lambda equal to 2 the mean is actually lower than lambda equal to 1, and your mean is lesser than for a predefined value. So that's why you are in the regime of rejecting the null hypothesis, so that it is making sense. That's all. Now let's do another thing. So it's testing. So here all the thing we do is the with simple hypothesis. Now if our hypothesis become composite, then what will happen, what will be the MP test, that we'll see. The testing for parameters of a normal population. So suppose x1, x2, xn follows, they all are independent and identically distributed random variable, and their distribution is normal with mu sigma square. Now let's see the testing. For the mean mu. Now here you see there can be two cases. One case 1, variance sigma square is known. So say sigma square equal to sigma 0 square equal to 1. Now here our composite hypotheses are, the null hypothesis is mu less than equal to mu 0, and alternative hypothesis is mu greater than mu 1. So you see here our hypotheses are not simple, because from the hypothesis we cannot determine the probability distribution. So if you see the null hypothesis, you will see that it is condition is mu less than mu 0. So this is a composite hypothesis. Composite and here the null hypothesis is mu less than mu 0. Now the test of size alpha, you see we have to check whether or not the mu is lesser than mu 0. Since it's dealt with mu, we have to use the sample mean, right? We have to use the sample mean, and we know that this sample mean minus suppose mu 0, and what we will check, that if mu is greater than mu 1. So let's see it pictorially. So suppose this one distribution, another, suppose this is another distribution. Suppose this is another distribution. Now suppose this is mu 0 and this is suppose this is mu 0. So suppose this is mu 0, suppose this point is mu 0. You see this is greater than mu 0, this is less than mu 0. Now you see that if my random variable E follows this red distribution, its sample mean should lie in the region. If this is mu, its sample mean should lie in the above this region, in this region. So sample mean should lie, its sample mean should larger than mu 0. So it should lie, if this is my null hypothesis, this is null hypothesis is this, that is less than 0. And when we gonna reject this hypothesis that my sample is my sample is collected from a distribution whose mean is higher than this mu 0, when each sample means is higher, that means here, that means let me use another color, sample means is suppose here. Now you see that if its sample mean is here, then we can say safely that it is not right to accept the hypothesis H0. So what will be the limit when we reject the null hypothesis. So that is x when x0 minus mu root n by sigma 0 is greater than z alpha. So then with let me write it here, root n x bar minus mu naught by sigma 0, if it is greater than a z alpha point, then we will say that we will reject the hypothesis with significance level sigma. So that is the test, and this is also true. This is the thing, and let me do another thing. Let me tell you another thing. Suppose that case 1, and if mu is greater than equal to, if my hypothesis is such that, then this will be my test, this will be my most powerful test, this will be my most powerful test. This is most powerful states. So that's all for today. In the next lecture we'll see other things, that if the other conditions, that is if for the other conditions, that is if for the case 2, if his variance is unknown, how you get the parameters, how your, and for other or composite hypothesis, how we will get the test. So that's all.